Okay, I think we started recording it. Great. So this is the last session of the day. It's on wireless. The first speaker is Pedram Sangdeh, and his talk is on LB-SciFi online learning-based channel feedback for MU-MIMO in wireless LANs. So let us hear from him. Thank you.
Okay, so I'll start. Hello everyone, this is Pedram Kheirkhah from Michigan State University, and today I want to talk about LB-SciFi and online learning-based channel feedback for multi-user MIMO in wireless LANs. LB-SciFi is designed for Wi-Fi networks, as Wi-Fi networks are of the great importance in today's society, and they are already carrying a massive amount of the data. Even the cellular networks are using to offload their data onto the Wi-Fi networks, and also new applications are being introduced to use the Wi-Fi networks. And also you can find the Wi-Fi hotspot everywhere in every shopping center, malls, dormitories, and stadiums. As a result, Wi-Fi networks are experiencing an exponential growth in their data traffic. And the real question is, how the Wi-Fi network can keep up with these growing demands, because this trend is expected to be continued in the next years. To address this issue, multi-user MIMO has been envisioned into Wi-Fi standards from 802.11 AC, and multi-user MIMO has shifted the communication paradigm from its traditional form, which was point-to-point. In the point-to-point communication, a single antenna AP was able to serve just a single station at a time. So the latency was high and the capacity was very low. In contrast, multi-user MIMO enables a multi-antenna AP to serve multiple stations at the same time. So capacity is much higher and latency is much lower. But the downside is that if for the beam steering, some sort of a spatial side information is needed at the AP side. And to capture this side information, those APs and stations will go through a series of interactions called sounding phase. During the sounding phase, first an AP sends a frame toward the stations. The stations estimate the channel, then AP pull the stations, and the stations will report the calculated channel to the AP. After that, AP calculates a spatial filter, and then the real transmission begins after this overhead. And unfortunately, this sounding phase can take even much larger than airtime than real transmissions. And it prohibits the real gain of the multi-user MIMO. So we should somehow reduce this sounding phase overhead to get the real potential of the multi-user MIMO. In this regard, some work suggests we should tune the sounding parameters. And the first step is exploring the underlying relation between the sounding parameters and the throughput, and then we can set the parameters optimally. Another direction is adaptive sounding frequency. So instead of having a fixed interval of the sounding, we can do the sounding adaptively, and we can leverage the CSI as long as they are valid. For example, in a static environment, we can use CSI for a longer time, and we can bypass some sounding phases and save the airtime. Another promising direction is implicit sounding. It means we can use the uplink CSI for downlink multi-user MIMO, but it needs additional RF chains and calibration to compensate the mismatch between the uplink and downlink channel. And finally, we have hybrid sounding, which means we can use a mixture of implicit and explicit feedback whenever it is possible. You can see limited progress has been made so far on compressing the CSI report itself, and all of this work are focusing on manipulating and adjusting the sounding interval instead of having an abstract representation of the CSI. Here, LB-SciFi steps in, and LB-SciFi has two phases, training phase and exploitation phase. In the training phase, an access point trains an autoencoder. An autoencoder is the core components of LB-SciFi here. While AP is serving the station in its regular manner, it collects the CSI, it trains the autoencoder, and whenever the AP finds that the autoencoder is working well in compressing and decompressing the data, it breaks the autoencoder in two parts, encoder parts and decoder parts. The encoder parts will be used for data compression and decoder part will be used at decompression. So it broadcasts the encoder part to the stations. At the same time, AP won't give up on improving the autoencoder. It continues to collecting the data and improving the autoencoder accuracy. And whenever it finds a great improvement in autoencoder, it rebroadcasts the encoder parts to the stations. At the exploitation phase, the stations and AP leverage the encoder and decoder parts. First, the station will estimate the channel based on the preambles in the frame received from the AP, and that channel gains shown here by H could be a very large complex valued matrix because the Wi-Fi standards employ a large number of subcarrier, and those large number of subcarrier can increase the size of the H. But fortunately, the standard won't use the H directly. It uses a mechanism called Givens rotation to translate that big matrix into a bunch of angles called psi and phi angles. These angles have all the necessary information for the beamforming, and it occupies less airtime than the H itself. So these psi and phi's are real CSI we have in Wi-Fi network instead of the channel gains. So in the exploitation phase, first the station estimate the channel. They use the Givens rotation to translate H to angles. The angles will be pre-processed and some pre-processing overhead will be introduced. Then the pre-processed data will be fed into the encoder. The result of encoder or code words will be quantized. Then the quantized value will be wrapped into the frame. Frames will be sent over the communication medium. And at the AP side, this frame will be recovered, dequantized, decompressed, post-processed. And finally, what we have is our estimated angles, and this estimated and recovered angles will be used for beamforming. So such a design is not that straightforward, and we face some challenges. And first is it should be fully automated because we want to finally implement that in a Wi-Fi network, and it shouldn't need any human intervention for supervision, correcting the performance of the compression and decompression and data collection. So it should be fully automated, and AP should take the full responsibility of all phases from data collection, training the autoencoder, broadcasting it, and also exploiting it. And also our desire is having a scheme that is transparent to the stations, because most of these stations in future are simple devices like IoT sensors, so they cannot afford a huge storage or a huge amount of the computational complexities. So, and finally, training a neural network can be very expensive in terms of the computations, but we want to have a scheme that is affordable for current devices on the market, and at the same time train an accurate autoencoder for compression and decompression. So the first phase is in having an accurate autoencoder is data collection, and in data collection, the AP should answer two questions. First, how to detect the meaningful and unmeaningful samples, and second, how to prepare a balanced and clean the data set. And these actions should be taken individually and independently by AP based on a single observation. And to do that, we introduced a metric called power spectral entropy. Power spectral entropy is a simple but yet powerful tool to enable AP to make decisions on observation basis. And to show how it works, we have an example here. imagine and time domain sequences like xn, and first we convert the xn into its spectrum using the FFT. The xk will be used to calculate the normalized PSD, and normalized PSD will be used to on entropy calculations. So in the formula we have here, you can see it's a normalized value between 0 and 1, and we have two extreme cases here. First is the DC signal. For the DC signal, the PSE will be 0, and another extreme case is pure noise. And for the pure noise, the PSE will be 1. And as you know, for DC signal is the most predictable and compressible signal. So the lower the PSE, the most compressible the signal is. And here, because this in the example, because our example has a noise-like behavior, its PSE is pretty high. Knowing the PSE, we can look into the features of the angles. As I said, these angles are the real CSI in the Wi-Fi network. We can see the statistic of this CSI. So you can see the psi angles and phi angles have different distribution and different PSE features. So here we decide to train two different autoencoders, one for each of these angles. So we train in parallel, and we collect the data and train two network autoencoder in parallel, one for each of these psi and phi angles. And you can see that the psi angles have lower PSE, so they are more compressible than phi angles, which have higher PSE. So now let's go back to our first challenge, which is detecting the meaningful and unmeaningful samples. And to do that, the AP should detect the garbage samples. And the garbage samples in the Wi-Fi network can generate a variety of the reasons, like failure in the time synchronization or failure in frequency offset compensation. And we have two examples here for a garbage psi angle and a garbage phi angles. What's common between these two garbage samples and all of the garbage sample we observed in a Wi-Fi network is the noise-like behavior they have. And due to this noise-like behavior, they have several dominant components in the spectrum. So the PSE is high, and this PSE of these samples can be used to block them. So we can set a threshold and block these abnormal samples by their high PSE. Now that we detected and blocked this garbage sample, we have a clean data set. And the question is it ready to train an autoencoder based off this data set? The answer is no, because imagine a typical wireless network, including an smart TV. The smart TV is there for a long time, so its historical data has high correlation. And after cleaning the data set, we expect to have a data set which is overoccupied by these static nodes. So if we train that data set for training an autoencoder, so that autoencoder highly likely works in favor of these static nodes because they overrepresent themselves. To avoid overrepresentation, we again use the PSE. So we calculate the PSE of the observation, and we divide the PSE range into multiple bins, and we choose, the AP choose actually. The AP choose a certain amount of the observation from each bins, and then we avoid overpopulation of the bins. So after this balancing the data set, we have a clear and balanced data set which is ready to train the autoencoder. And we do the pre-processing on top of that. We make the data zero mean and uniform variance over the feature, and here the features are the subcarriers. And then we have a data set ready to train the autoencoder. To train the autoencoder, we have multiple factors to decide about the architecture of the best autoencoder. But the most dominant factor here is the dimension of the latent layer called code layer. And that defines the trade-off between compression ratio, and compression loss. As shown in these figures, you can see a good trade-off point here is code dimension of 3 for psi angles and code dimension of 8 for phi angles. And the networks that result this good trade-off are shown here. You can see we can use a smaller neural network autoencoder for psi angles because remember they are more compressible, and we can converge this network with a smaller number of the samples. And on the contrast, phi angles needs a bigger network because they are less compressible and they converge with a larger number of samples. So the training time will be defined by the psi angles. This network will be used to implement the LB-SciFi, and we have prototyped the LB-SciFi on a real wireless testbed. In our testbed, we set the sampling rate to 20 megasample per second, and also carrier frequency is set to 2.4 gigahertz to avoid unwanted interference from the real Wi-Fi networks in a surrounding area on the campus. As equipment, we use USRP N210 for data transmission and reception. We use the clock to synchronize different antenna at the AP side, switch to collect the data, and PC and laptops for baseband digital signal processing. For the metrics, we use error vector magnitude, gross throughput, which is actually the over-the-air throughput, and net throughput that considers the airtime we spend to get the gross throughput. For the compression performance, we compared LB-SciFi with the existing settings in the standard, then those settings can be named T, I, G, J for feedback type I and J tone grouping. There are two types of feedback in the standard, type 0 and type 1, type 0 for low resolution feedback, type 1 for high resolution feedback, and there are three options for subcarrier grouping, 1, 2, and 4, to have a couple of subcarriers as one group. So for the baseline, we have T1, G1 for accuracy because it has the highest accuracy and the largest overhead. And for the compression, we have T0, G4 because it has low resolution and highest subcarrier grouping. So it entails the lowest accuracy, but at the same time, lowest overhead. And we can see, if we compare the LB-SciFi with the existing setting, we can see in the terms of the error, LB-SciFi is better than any compression in the standard, but it is slightly worse than T1, G1 and T0, G1. But we should remember, these two settings do not perform any compression in the frequency domain. So they have a very high overhead. In terms of overhead, LB-SciFi is better than all the settings in the Wi-Fi standard. So we can claim that LB-SciFi is more accurate than any compression protocol in the standard, and at the same time, it entails the lowest overhead. To go for more detail, we have a case study here. In the case study, we have fixed 3 stations across the floor plan. We fixed the AP at the middle of the floor plan. AP has 8 antennas and the stations has single antenna each. We shown the constellation of the receive signal at the stations from the AP, and you can see the constellations are relatively clear and easy to recover the original signal. And for average EVM, you can see the LB-SciFi is far better than T0G4, but it's slightly worse than T1G1. But T1G1 cost us a lot in terms of the overhead. And that is why the overhead of the T1G1 differs its throughput. And finally, LB-SciFi shows 68% gain over T1G1. And at the same time, because the T0G4 was inaccurate, the LB-SciFi shows 41% gain over T0 and G4. We extended our experiments to a more generic case for a 3-user MIMO when an 8 antenna AP serves 3 stations, and once again you can see that LB-SciFi shows a great gain. We repeated the same experiment for 4-user case, And again, LB-SciFi offers 28% gain over the T0G4 and more than 100% gain over T1 G1. So I've shown that the LB-SciFi is a generic framework and it needs a couple of the thresholds. And those thresholds should be set inside the environment because those are specific to the environment. And LB-SciFi cannot offer universal numbers for those thresholds. But the good news about LB-SciFi is that LB-SciFi is of a low overhead and it shows a significant gain. It has a good compression ratio and low compression error. So LB-SciFi can be regarded as a promising solution for future Wi-Fi networks. Thanks for your attention, and it's my pleasure to answer your questions.
Okay, thank you very much for your talk. Do we have any questions from the audience?
Yeah, sure. Hi, this is Kunal Sankhe. So the question is specific to your experimental evaluation. So you mentioned that your access point as well as stations were implemented using USRP, and I think you captured traffic in 2.4 gigahertz using USRP. Is that correct?
Right.
So my question is, how did you make sure that while collecting the data, you are not collecting data which is from the existing actual COTS access point? So how did you make sure that while you're collecting the data, you are not collecting data not just from your own station, but also from the other commercial devices?
Yeah, very good point. Very good point. First, we observed the spectrum and we observed that there is no other occupant in that spectrum. And second, to has another measure to counter unwanted interference, we used a unique preamble into our frames. So and it was different from the existing Wi-Fi networks. We made a PN sequence as a preamble, so we couldn't detect if we get any signal from others. So we used that unique preambles and unique value to synchronize and detect our frames.
Okay, do we have any other questions? Okay, I have one quick question. So you are basically...
I lost my connection.
So are you lost? Do you have anything follow up?
No, I think I lost my connection. I couldn't hear. If it is okay, would you be able to repeat your answer?
Oh, yeah.
Sure. As our first countermeasure, we observed the activities on the spectrum, and we conducted the experiment when we make sure that the spectrum is free of other unwanted occupants. And as our second measure, we used a unique PN sequences in our frames for synchronization and other stuff. So our AP and the station wasn't able to detect any signal other than what we wanted.
Okay, sounds good. Okay, thank you.
You're welcome.
Okay, so how do you deal with the computational complexity of your training at the access points?
We couldn't measure it on a real modems because we couldn't implement our algorithm on ARM processor. But roughly, we calculated that for training the neural network autoencoder based on what we have in our environment, we need 40 million calculations. And based on the capability of the current ARM processor in the market, it takes a time in order of milliseconds. And theoretically, we proved that it works. But in terms of the real experiment, no, we couldn't implement our networks on a real Wi-Fi, a real access point.
So what is the reason that you couldn't do that? Because
we couldn't actually, yeah, we couldn't implement the machine learning package like we used the PyTorch. We couldn't implement the PyTorch on the ARM processor.
Okay. Okay. Yeah, I know these things are different. Yeah. Okay.
Yeah.
Okay. Enough. Any other questions? Do we have anything on the chat, or let me check? Okay, I think no. So if we don't have any other questions, we can start the second talk. Thank you very much again for the talk. It was a very nice talk. Okay, maybe Suresh can start sharing his screen.
Sure, Hulya. I'll just start.
Okay.
Please let me know if you can see my screen.
Yes, we do. Yeah, everything works well. Okay. Our second speaker is Suresh Srinivasan from Portland State University, and the talk is on fair initial access design for millimeter wave wireless. Thank you.
Hello, everyone. This is Suresh Srinivasan from Portland State University, and I'll be presenting our paper, Fair Initial Access Design for Millimeter Wave Wireless. So millimeter wave is an essential component for the next wireless technology. So millimeter wave operates in the band of 25 gigahertz to 300 gigahertz. So when we use a conventional omnidirectional antenna for millimeter wave communication, it suffers from high path loss and are susceptible for the blockages. To overcome these shortcomings, millimeter wave adapts a directional beam communication. With the use of directional beam communication, clients need to perform their beam training to select an optimal beam for communication. When multiple beams perform their beam training simultaneously, the near clients power dominate the farer clients, resulting in an unfair initial access. The existing standards such as 802.11ad and AY performs its beam training during an initial access. During the initial access, first AP performs its beam training by transmitting sector sweep frames across its sectors in all directions, and the client records the SNR of the received beams. Next, the client performs its beam training by transmitting its beams across sector sweep frames across its sectors in all directions, and the AP records the received SNR beams. Again, when multiple clients perform their beam training simultaneously, it results in an unfair initial access. 802.11ad and AY defines a beacon interval, which is subdivided into two subintervals: one, beacon header interval; two, data transmission interval. AP discovery, beam training, control, and management information exchange are performed during the beacon header interval, and data communication is performed during the data transmission interval. And data communication and DTI supports different types of medium access protocols such as TDMA and CSMA. Further, BHI is further subdivided into three subslots: one, beacon transmission interval; two, association beam forming training; and three, announcement transmission interval. So during the BTI, AP performs its sector sweep by sending its sector sweep frames across the sectors in all directions. And during A-BFT, client performs its beam training by transmitting its sector sweep frames across its sectors in all directions. And during the ATI, AP exchanges management information with the associated and beam trained clients, such as an optimal beam and the mode of DTI communication. So what we saw so far is about millimeter wave and the use of a directional beam communication, and the initial access, and when multiple clients accessing simultaneously, it results to an unfair initial access. And also we saw about 802.11 AD and AY. Now we go into motivation, like, what is the prevalence of this contention imbalance and how do we quantify? To understand the prevalence of contention imbalance, we set up a millimeter wave wireless LAN using commercial off-the-shelf devices such as AD7200 router and Acer TravelMate laptop. So we set up the millimeter wave LAN at location 1,1 and connect the near client, which is an AD7200 configured as a client, and let the client connect to the AP and record the SNR of the beams received at the AP. And we place the forward client, which is an Acer TravelMate, across X, Y across various grids and record the SNR of the beams received at the AP. So currently, the AD7200 router firmware neither logs or records the SNR beam received at the AP. So we modified the AD7200 router firmware with the NetWan framework to enable SNR logging of beams received. So the clients which we used were AD7200 and TravelMate. It uses 36 beams with a beam width of 10 degrees. A typical SNR variation of the beams received at the AP is shown in figure B. Now, how do we quantify this unfairness, that is a computation unfairness? We use a metric of computation fairness index, for which we set up a AP in grid number 1, which is an AD7200, and place a client in grid 1,1 and let it connect to the AP and record the SNR at the AP, and place a forward client in different locations X, Y, and record the SNR received at the AP. So once we get all the SNRs of the beams, we compute the computation fairness index using this equation S other of J divided by S near. So what is this S near? Is the total number of beams for which the power of the beams between the near and the adjacent grids beams are at least greater by 3 dB. Once we compute for various locations, we plot a heat map as shown in the plot, and we see that the grid 1,1, 2,1, and 2,2 are dominating with all other grids, creating an unfair, unbalanced fairness. So the degree of throughput unfairness depends on the frequency of clients' participation in the A-BFT. Suppose there is one A-BFT slot and there is one client, near client, and one for client participating in the beam training, then and if near client and for clients participate in all the A-BFT, then the near client would power dominate the forward client, resulting in forward client never participating in the beam training. So we did many experiments to characterize what is the cause for the client's participation in A-BFT. So most predominant causes of the client participation in A-BFT are mobility, blockages, sporadic traffic, association to the new IP. So what we saw till now is the motivation, like prevalence of the contention imbalance. We derived a metric for competition fair unfair imbalance, and we saw how the unfairness prevails and also the frequency of participation. Now we propose a new algorithm to overcome this unfairness, initial access unfairness, called JPOC. So to optimize or to improve the initial access unfairness and to improve contention adaptation protocol optimization, we propose joint power control contention adaptation protocol, JPOC. To summarize JPOC in a nutshell, JPOC scales or reduces the power of the clients so that fewer beams are received at the AP. So what is it? So what's so great about this? So when you reduce the number of good beams at the AP, it reduces the number of interference with the forward clients. So with JPOC, the advantages or the gains are it lowers the interference between the near and far clients, it increases the IA fairness and decreases the number of slots. So as we talked that the JPOC is trying to reduce the client power and reduces the number of beams received at the AP, for which let's assume the AP desires a desired SNR of beams at the AP, and we call that as a gamma. So then the gamma is equal to the maximum power received minus the noise power. So the maximum power that an AP would expect at an AP would be an gamma plus the noise power. So now the most key point is, how does the client know what is the power that it needs to transmit, and we do not know which beam is the optimal or the good beams that's going to be received. So we use use path loss equation, which is power max at AP is equal to power transmitted at the client plus the beam forming gain of a beam I at client plus the receive gain of AP minus the path loss. Similarly, we have the maximum client power received the client when the AP performs its sector sweep is given by transmit power of AP plus the gain of beam gain of AP plus the receive gain of client minus the path loss. Next, by using these two equations and subtracting them and rearranging, we can derive a power of client, transmission power of client, which is given by maximum power received at the AP, which is actually gamma plus the noise power, which is an expected power, which is known. Next is the maximum power received at the client, which is known when the AP performs its beam training, plus the array gain of the client and the plus maximum array or beam forming gain of the AP antenna array. So the AP will add this maximum array or beam forming gain of the AP during its BTI, during its SSW frames, that is sector sweep frames during BTI. So the existing 802.11 AD and AY proposes slots and subslots for A-BFT, which is an overhead. So JPOC proposes to use mini slots only. JPOC determines the mini slots dedicated to an A-BFT and announces during the BTI interval. Suppose there are m number of subslots in an A-BFT, and there are clients 1 and client 2 with b number of sector sweep subslots, then the clients performing its beam training would reduce, using this b number of subslots would reduce the interference between the clients as shown in the figure. So another very important estimation is our optimal beam estimation, which is M-opt. So M-opt is, let's assume we have K, the number of good beams, and let N be the number of clients contending during A-BFT, and P0 be the probability of the client that participate participate in A-BFT cannot establish a connection with the AP. Then with these parameters, we derive an optimal mini slot M-opt as k by 1 minus p naught to the power of 1 by k whole to the power of 1 by n minus 1. Here we assume that the k, the good number of beams, to be even across the clients, and the non-good beams do not interfere with the good beams. So what we saw till now was the design of JPOC. The intention of the JPOC was to improvise the initial access fairness and to improve contention adaptation protocol, for which we proposed how to reduce the power at the clients and to use the mini subslots instead of using a subslot for beam training. Next, we'll be talking about the performance evaluation of JPOC on initial access fairness and contention adaptation protocol. So to understand the effect or the impact of JPOC on the number of good beams, we did set up a millimeter wave LAN wherein we placed AP at AP, which is AD 7200 at location 1,1, and we placed the for client, which was a ASA travel mate, at every other location X, Y, and recorded the SNR of the beams received at the AP in grid 1,1. So we did this characterization using 3 different modes. One was without power control and with power control and gamma equal to 10, and third one with power control and gamma equal to 4. So we did plot the number of good beams received at the AP in 6 different brackets. One was 1 to 6 to up to 31 to 36. So first, when we perform the characterization with the client, with the for clients, with the clients without power control, we saw that the beams were evenly distributed across all the brackets from 1 to 6 to 31 to 36, as you see the blue chart here. So next, what we did is we adapted the power JPOC with the power control and a gamma of 10, and we eventually saw that the good beams were more focused towards 1 to 24 bracket. So you see the orange one. So next, we further reduced the gamma to 4, and we saw that the most good beams were mainly focused between 1 to 12. So this shows that the JPOC has a substantial effect on the good beams. Now, next, we study the effect of JPOC on the fairness enhancements. So we've been talking like JPOC is going to have an effect on the fairness index. So what we did, as we discussed earlier, first we set up a millimeter wave LAN with one AP AD 7200 and two clients, one with AD 7200 as a client and another client as ASA travel mate. First, we locate the AP at grid location 1,1 and place the client near client AD 7200 configured as a client in location 1,1 and move and let the client connect to the AP and record the received SNR at the AP and place the forward clients at every X, Y location, every other location in the grid, and record the received SNR beam at the AP. And we use the computation fairness index to compute the fairness, first under 3 different configurations. One without power control, next with power control and gamma equal to 10, third one with power control and gamma equal to 4. First, without power control, you see that 1 to 3 blocks were power dominating all other grids or all other locations. As we introduced the JPOC power control with a gamma of 10, we saw at least 8 of the blocks were getting better fairness as compared to the other grids. And as we increased the gamma from 10 to 4, we see that all the blocks, most of the blocks were getting a fair access. So this shows that JPOC had a effect on the initial access fairness. Next, we ran the simulation with the millimeter wave LAN with n number of clients and k number of good beams, and evaluated our analytical model with the simulated model and plotted the failure rate and the number of mini slots estimation and the number of clients, and found that the analytical model was closely matching the simulated values as shown in the figure. Further, we compared the fairness, we used Jane's fairness index to compare the JPOC and 802.11 AD and AY. So when we increase the blockage probability, we saw that the 802.11 AD started to deteriorate or gave a unfair initial access as the blockage probability was increased. So as compared to JPOC. So JPOC performed much better, which was giving a much fairer initial access as compared to 802.11 AD with the 9 to 12 times lesser overhead as compared to 802.11 AD and AY. Now, we did do the initial research on the existing research of work on optimal beam selection, and we found that predominantly there were four sections that was researched. One was beam search techniques, out-of-band beam selection, proactive beam adaptation, and environmental sensing. So all these techniques was to train the beams using codebook techniques, or to select an optimal beam using out of band like Wi-Fi, which is out of band, and you figure out what is the optimal beam that might come out, and proactive beam selection. So like it was trying to proactively monitor the existing beams and obstacles to predict what could be the next optimal beam. But all these techniques propose what could be the beam, but never addresses the unfairness, initial access unfairness. To our best of our knowledge, JPOC addresses the initial unfair access and proposes how to enhance initial access and improvise contention adaptation protocol optimization as well. So in summary, we showed that as clients train their beams, there exists a severe imbalance coupled with contention protocol design, resulting in an IA unfairness. We also proposed an open loop joint power control and contention adaptation protocol to address the unfairness, initial access unfairness problem. We showed through experiments and simulations that compared to 802.11 AD and AY, JPOC substantially increases the fairness and reduces the contention overhead by 9 to 12 times. Yeah, thank you. I'm open for any questions, please.
Thank you very much for your talk. Do we have any questions? So I can also check the, let's see if we have anything on the chat, session Q&A. Okay. Okay, if not, let us thank the, Suresh again, and we can start the next talk.
Thank you, Leah. Thanks for everyone for listening. Thank you.
Thank you very much. So our third speaker is Sabbir. So maybe he can share his screen.
Yeah, hi. Can you hear me?
Yes.
Okay. Can you see my presentation slides?
Yes.
Where does it go? Okay. You can see it now, right?
Yes, we can see it. Okay. So our third speaker is Sabir-Saadat from University of South Carolina, and his talk is on a case for temperature-aware scheduler for millimeter wave devices and networks. Thank you.
All right. Thank you, Hulya, for the introduction. All right. I'll start. Hello, everyone. I'm Sabir-Saadat, a second-year PhD student at the University of South Carolina at the Computer Science and Engineering Department. Today, I'll be presenting our paper, A Case for Temperature-Aware Scheduler for Millimeter Wave Devices and Networks. I've divided my presentation into 5 distinct sections. First of all, I'll explain what necessitates a completely new technology for the next generation wireless networks and why millimeter wave is a suitable choice. Next, I'll introduce our audience to the phenomenon of device overheating in millimeter wave networks, a quite prevalent and yet unstudied phenomenon. I'll then be presenting the results we obtained from the thermal characterization study we conducted on a 60 GHz millimeter wave mobile testbed. Following thermal characterization, I'll present Etilo, which is an antenna scheduler for multi-antenna millimeter wave systems as a means to combat device overheating. Lastly, I'll conclude this presentation with a brief discussion of our findings and contributions. So let's see why 5G requires a complete overhaul of our wireless infrastructure. The demand for wireless data is not only at an all-time high, but it is projected to increase exponentially in the coming decade. By the end of this year, it is estimated that the number of 5G subscriptions will reach 190 million and increase by 10 times in the next 4 years. The simple reason is the increasing ubiquitous wireless connectivity of our everyday items, from smartphones and tablets to cars, TVs, and refrigerators. This overwhelming web of wireless nodes of everyday items is what is being dubbed as the Internet of Things, or the IoT. This increasing wireless connectivity imposes several stringent requirements on our wireless networks, namely, first, multi-gigabits per second throughput to support all the increasing wireless nodes, and an expanded bandwidth and ultra-low latency, both to support all the new applications coming into the wireless networking realm. For examples, the immersive virtual and augmented reality demand more than 5 Gbps wireless speeds and sub-10 millisecond frame transmission latency. An autonomous car at its peak rate can locally generate 10 Gbps data from its various sensors. All these requirements necessitates a new enabling spectrum. If you look at our current microwave spectrums, namely the LTE and Wi-Fi bands at 2.4 and 5 GHz and such, this is how much we have in terms of bandwidth. This supports sufficient throughputs for 4G networks, but not so for 5G. Compare this to the much wider, almost hundreds of times larger available bands of unlicensed spectrum. This is what we call the millimeter wave, alluding to the order of the wavelengths in this band of spectrum. This band supports throughputs of multiple Gbps and enable the ultra-low latency connectivity that we desire for 5G. Specifically, this blue slice of almost 7 GHz within this large band is being incorporated into the latest IEEE 802.11ad standardization. Just as with any new technology, incorporating millimeter wave into the wireless networks has meant overcoming several challenges. Research in millimeter wave has been ongoing for a while, and most of these challenges have sound research background in the existing literature, except the overheating of millimeter wave devices. Our focus in this work is to gain more knowledge about this issue and seek ways to mitigate it. In fact, our investigation with a 60 GHz Rogue smartphone reveals that temperature starts increasing immediately on power up. In this setup, we demonstrate how the temperature of the outside surface of a 60 GHz Asus Rogue smartphone increases through a reel we obtained from a thermal camera. The white circle shows the location of the 60 GHz antenna. Heat distributes from the antenna region over the entire surface of the device immediately on power up. There's already 7-degree increase in temperature just within 2 minutes, and by 5 minutes, temperature can reach abnormally high, almost 11 degrees above the resting temperature. Indeed, overheating of millimeter wave devices has been reported by several tech outlets, specifically in the last 1 year, showing us clearly there is a research problem at hand that needs to be solved right away before 5G is widely deployed. The issue with device overheating is twofold. Firstly, overheating of devices used near face and brain imposes potential health hazards as well as causing user discomfort. Next, the network performance is also degraded as the higher temperature causes a higher noise and leakage current, leading to large fluctuations in throughput. Despite such prevailing issues with device overheating, the characterization of thermal behavior of devices under millimeter wave network is non-existent in the literature. Hence, we carried out the first investigation of such a kind on our millimeter wave testbed. Let's check our findings. Our measurement testbed consisted of a Nighthawk X10 router as access point and an Asus ROG smartphone as the mobile node, both capable of working on a 60 GHz spectrum. The setup allowed us to transmit data packets from the access point to the smartphone and measured the corresponding system throughput achieved as well as the resulting temperature of the smartphone antenna chip with fine granularity. Indeed, our measurements have revealed quite large fluctuations in throughput while network strength remained largely stable. In one measurement over 90 seconds, the throughput series showed standard deviation as high as 240 Mbps, while the strength of the link at which the throughput was achieved remained steady at -64 decibel. While we have seen the temperature remains steady at 47-48 degrees region in the idle powered on state, it keeps increasing with data transfer before plateauing off at a higher temperature. The higher value at which the temperature plateaus off increases with average throughput. In order to study the dissipation of the stored heat, we carried out several trials with fixed periods of transmission and then allowed the device to cool down. We show here one such 10-second transmission trial. It is seen that while temperature increases rapidly with the beginning of transfer, it does not fall back immediately. Rather, heat in the antenna chip acts as charge in a capacitor. Moreover, our studies indicate that both the rising profile and the falling profile of the temperature can be modeled as separate exponentials, as an exponential rise and an exponential decay. A naive way to prevent overheating of a device is to induce idleness in between periods of data transfers. The idleness allows the antenna chips to cool down. We investigated such a scheme. The access point transmitted packets for 10-second intervals repeatedly, interleaving 5-second idle period in between each transfer. The total operation time was 270 seconds, thus the effective period of operation was 180 seconds, with 66% duty cycle. We compared this with a 180-second continuous transmission and a 270-second continuous transmission for the sake of completeness. While the continuous operations cause the temperature to reach 75 degrees Celsius within 150 seconds, the trial with periodic idleness never crosses the 65-degree mark. Such a naive scheme, however, is inadequate for two reasons. First, even small transfer duration and high idle period cannot substantially reduce the peak temperature. Moreover, latency critical and throughput hungry applications require continuously high throughput. These applications such as virtual reality, real-time gaming, or tactile internet with their high requirements of high throughput and ultra-low latency do not allow buffering of their data. Data transfer is required on demand.
We started a little earlier also because our presentation was there. So, earlier start.
Excuse me, I think, okay.
Excuse me?
So there was a noise background. So, okay, I think he muted it. Thank you. You can go ahead.
Okay, just a thing. Can you hear my, can you see my full presentation slide?
I can see it, yes.
Oh, okay, thank you. Yeah, I
Yes.
was like worried because anyway, so I'll continue then. Thus, to allow an antenna to periodically go to sleep mode while preventing any idleness in the data transfer, we must switch operation between multiple antenna units placed on the device. Fortunately, this is the likely reality in the coming days as multi-antenna design is increasingly being suggested by industry experts as the means to improve network reliability in the reality of rampant signal outage. Aquila achieves this switching scheme between the antennas in a smart way so as to achieve the most reduction possible in temperature without causing throughput to drop below the application requirement. The switching is achieved on a temperature awareness basis. The switching of the antenna units is not naive. Neither are simple random switching nor one that maximizes throughput by always selecting the antenna with the best link can achieve any near optimal temperature reduction. Furthermore, there are two challenges we must confront. First, millimeter wave channels are very unreliable as signal outage is very frequent due to both blockage and node mobility. While this has made the multi-antenna design attractive, which is good news for us, but this also means that one cannot simply schedule antenna in terms of temperature optimality. For example, just the tip of the user's hand can completely kill link connection. Secondly, our investigation reveals that a completely predetermined temperature model cannot be derived. For the same device, temperature model is highly dependent on the surrounding temperature as well as insulation condition and user handling. As is shown by these example thermal profiles we obtained with the same device at two different locations, an office environment and a home environment. Clearly, the thermal profile obtained from home shows both faster increase and faster decrease in temperature. These challenges impose us to design a kilo with these design components. Let us see what each of these components achieve. The online thermal profile estimation is the estimation of how temperature at each of the multiple antennas rises during transfer or falls during idle period. Our investigation revealed that this rise and fall can be modeled with separate exponentials, an exponential gain for the section with data transfer and an exponential fall for the section in idleness. The model parameters in a kilo are derived from online measurements of both the active and the resting antennas in the background. The online estimation of the thermal profile helps a kilo to estimate the peak temperature that would be reached by each combination of antenna schedule. A kilo executes just that task, generating a list of look-ahead schedules with the respective peak temperatures. For instance, in a system with 4 slots, this is a likely list of look-ahead schedules. So this is how the tasks are scheduled in a kilo. The look-ahead schedules generated at an earlier frame are sorted at the beginning of a later frame. The sorted schedules are used to schedule the antennas in each slot of the later frame. Note that during the sorting process between 2 frames, data transfer does not have to stop, and hence it does not cause any latency. The only source of latency in a kilo is the beam alignment of the antennas at the beginning of each slot. One rule that a kilo follows in generating the list of look-ahead schedules is the non-adjacency criteria, which states that no antenna can be scheduled in consecutive time slot. Hence, the first 2 schedules on the left are valid. The third schedule is invalid as antenna 3 is scheduled in both second and third slot. Fourth schedule is valid as well. This criteria helps to reduce the size of look-ahead schedules by eliminating those schedules which do not allow an antenna to go to sleep mode right after an active mode. Let's now compare and evaluate a kilo with other antenna scheduling schemes. The most logical antenna scheduling scheme would be one that optimizes the throughput. Hence, we first investigate how much peak temperature can increase in a throughput optimization scheduler. We see that such a throughput optimizing scheduler causes the peak antenna temperature to rise as high as 70 degrees just within 90 seconds of operation, while average throughput is maximized, the resulting fluctuation degrades network performance. Then we investigate how much peak temperature can increase with a kilo under the same set of conditions. A kilo keeps temperature within a tolerable 55-degree range, achieving a reduction of 16 degrees compared to the throughput optimization scheme. Note that a kilo achieves this temperature reduction, maintaining the minimum required throughput level. Hence, the sacrifice in not following a throughput optimal scheme does not hurt the running application. We carried out further investigations to compare a kilo with several other antenna switching schemes to see how much temperature reduction is achieved. We first run a best case impractical antenna scheduler which searches through every possible schedules and choose the one generating the least peak temperature. We then run a random scheduling scheme which, as the name suggests, randomly selects any one of the antennas at each slot. Then we run a switching scheme which randomly selects an antenna but maintains the non-adjacency criteria, a design component of a kilo that we have seen a little while earlier. We run this scheme to determine the temperature reduction capability of non-adjacency criteria itself and itself alone. Finally, we run a switching scheme which schedules the best link strength antenna and thereby maximizes the link throughput. We compared how much temperature reduction is achieved by kilo in relation to the other schedulers by running each of the schedulers for several trials. We first compare a kilo with the best case scheduler. We see that a kilo achieves temperature reduction just within 1 degree of the best case, most optimal scenario in a median case. Then we compare a kilo with the other antenna schedulers, showing us clearly how much temperature reduction improvement can be achieved by a kilo over the other schedulers. At the same time, we computed how much throughput is achieved by each of the schedulers. First, a kilo's throughput is compared with the throughput optimization scheme. We see that the sacrifice in throughput by a kilo is only 10%. Then we compared a kilo's throughput with those obtained from the other schedulers. We see the Akilo's throughput very much matches the throughput with the other schedulers. While Akilo achieves minimization of antenna temperature, it may do so at the expense of some throughput. Some applications, however, require continuously high throughput. We tested while running some of these applications, such as FTP and VR. We first checked the throughput performance of Akilo. This shows us that Akilo, while minimizing antenna temperature, also ensures that the applications run with their minimum throughput requirement. Then, in terms of temperature reduction, we see Akilo achieve substantial reduction in antenna chip temperature compared to other schedulers. So to summarize this talk, in all, we have come to the following insights and achieved the following contributions. We have seen that overheating of devices under millimeter wave networks is quite prevalent and poses potential health hazards as well as degradation in network performance. Moreover, we have seen that such an issue is not a trivial problem to solve due to both unreliable network connectivity and the infeasibility of deriving a deterministic temperature rise and fall model. We have based our solution to the above problem to a thorough study of the thermal characterization of devices under millimeter wave networks, which is the first of its kind in known literature. Based on our insights, we propose Akilo, a temperature-aware multi-antenna scheduler for millimeter wave devices. We've seen that Akilo achieves substantial reduction in chip temperature within 1 degree of the best case, most optimal scheduler, while at the same time supporting the requirements of the running application. Thank you everyone for listening. We thank our sponsor, National Science Foundation. You can check our full paper at the ICNP website, and I can take your questions now. Thank you.
Okay, thank you very much. Any questions?
Hello, this is Simon speaking. I want to ask a question about the evaluation. So in your evaluation, how many positions did you test?
How many?
How many positions of the device did you test?
Oh, okay. So we tested for, in terms of positions, you mean the orientation of the device?
Yes, orientation and also the position of the device. Let's say the distance between the device and also the
So we tested, let's say we had, when we are testing for different throughputs, we had the device at different distances as well as different orientations. So we were testing at 4 distances, and at each distance we had I think 10 positions. So that each of them gave us like different throughputs.
Okay. And also, I mean, have you tested any mobile scenarios? I mean, when you move the device, I mean, continuously.
Yes, we did. I don't think we had in the paper we had a mobile. No, we had evaluation results for mobile nodes. I don't think it's here.
And if I remember right, I don't see the results in your slides.
No, mobility results is not there in the slides, but it's there in, like, for the sake of space, we cut it off. But in the paper, it's there. We have results for mobile nodes.
I have another question about blockage. You also mentioned that actually blockage is a very important, is a very big change in millimeter communications. And also, I mean, in your scheme or in your evaluation, have you also tested the scenarios where you have blockages? Maybe in some if there's some blockage, maybe because you have 4 antennas, maybe some of those antennas don't work in some scenarios.
you mean, did we check whether, did we check experimentally? Like, we actually didn't like practically checked for blockage, but we did ensure that there was no blockage, and we modeled blockage in terms of, so when we were, working with the measured data, we modeled blockage as in, so we say that at any given time, an antenna has 0.1 probability of blockage. So we didn't actually, blocked an antenna or created a situation where the antenna is blocked. When we took the measurements, the antenna had, we ensured that there was a channel, but when we simulated the results, then we actually, modeled a blockage probability.
So in your simulation, maybe you assume that one with antenna, maybe it doesn't work because of blockage, right?
Yeah. So let's say it's running for 100 seconds, and at let's say it's running for 100 seconds, and there is a slot at 10-second intervals, and when it's switching to a different antenna at every slot, we set a blockage probability. Let's say when it's trying to switch to antenna 2, then there is a blockage probability of 0.1. So there is a probability that antenna 2 is not, does not have a channel. So we cannot switch it to antenna 2.
Okay, I see. So may I ask another question?
Yeah, sure.
Okay, so can you go to a slide 32?
32?
Yes.
Yeah.
Because here you mentioned that at home, actually you see the temperature increased faster than when you have the experiment at office, right? So
at home.
Yes, at home.
Yeah.
It increased faster. Yeah. Do you know why? Why is the temperature increase faster?
Yeah. So yes. So this like rise and fall, this actually depends on the environment as well as the handling of the device, or as well as the insulation of the device, the condition of insulation. So if your environment itself is, let's say your home environment is much cooler than office environment, there's a much greater temperature gradient, right? So due to temperature gradient, your temperature will fall faster.
Okay.
And temperature rise can be faster because of higher throughput. But so these are the factors which come in terms of how fast the temperature will increase or how fast it will decrease. So that's basically, yeah.
Okay, thank you.
Okay, thank you for the questions.
Okay, any other questions?
Yeah.
Okay, let us check if we have anything through chat and session Q&A. I don't see anything, I guess. Okay, if there are no other questions, let us thank Saadat. And I think this is the end of today's session. Thank you. I'm not sure if the organizers have any announcements. If not, so this is basically what we have in this session.
Yeah, we can conclude. I think it's over for most of the people. I think the local people can still benefit from the in-person component of the conference, but I think the rest of you have to do it on your own to celebrate the banquet of ICNP. Okay, see you all tomorrow.
Okay, thank you very much, everybody. Bye.